Greetings of the day to all of you. Today we are going to learn about matrix converters. It's going to be an introductory lecture on matrix converters. I believe I have already introduced this converter topology to you in the last semester in our course on applied power electronics. However, this lecture is going to be a little more detailed as compared to the previous lecture. So basically, what are matrix converters? They belong to the class of AC to AC converters. So you have direct conversion from three-phase AC or polyphase AC to again polyphase AC at variable voltage and variable frequency. The advantages offered by matrix converters as compared to classical cycloconverters, which are also AC to AC converters but they use thyristors, is that matrix converters offer unrestricted frequency conversion, which means you can attain any frequency irrespective of the frequency of the source. You will attain any frequency at the load side irrespective of the frequency of the source side. Now the circuit shown over here is the circuit of a three-phase to three-phase matrix converter. You have a three-phase AC supply available with a fixed frequency and a fixed magnitude, and at the output, which is small alphabets ABC, you can attain three-phase voltage at any of any magnitude less than the magnitude of the input and at any frequency. The converter limitation is that the maximum voltage available at the output of the converter is only 86.6% of the input voltage. So the voltage transfer ratio of the converter is limited to 0.866. Anything between 0 to 0.866 times the input can be made available at the output. Now, the basic idea behind a matrix converter is that you have three groups of switches and each group has three devices. So you have switches SAA in the first group, which basically samples the input phase capital A at the output phase A. This switch SBA samples the input phase B at the output phase A, and the third switch SCA samples the input phase C at the output phase A. Similarly, ABC of the input can also be sampled at the output phase B through switches SAB, SBB, SCB. Right, and finally the three input phases can also be sampled at the output phase C, again through three switches AC, SBC and SCC. So you have a total of 9 devices in a matrix converter. Now this was about the basic principle of a matrix converter, that any input phase can be brought at any output phase by means of this array of switches, or a matrix of switches as you may call it. Let's talk about the switching states of this converter. Now, we know that there are 9 switches, and we also know that each switch can be on or off. So either let's talk about SAA. It can have two possible switching configurations because it can be either on or it can be off. Similarly, SBA will have two switching configurations, SCA will have two switching configurations, so on and so forth. So a total of 2 raised to the power 9, this will happen 9 times. So a total of 2 raised to the power 9 switching states, which is 512 switching states, are possible in this converter. This is primarily because the converter has a large number of devices. Therefore, theoretically, it is possible that 512 switching states can exist. However, all of these 500 switching states are not feasible in case of a matrix converter. There are certain switching rules that the matrix converter has to follow. The first switching rule is that the converter cannot be given those switching states that can cause the input voltages to be shorted. For instance, it is not possible to, the first rule is that the input phases should not be shorted. For instance, I switch on SAA as well as SBA, which means that the two phase voltages VAA and VA and VB input phase voltages have been shorted by means of these two devices. So that's like a dead short circuit condition. It will cause a lot of current to flow through the converter and the devices will get damaged, of course. So this condition has to be avoided, which means that in any group at a time only one device has to conduct, right? So only SAA or SBA or SCA has to conduct, which means that only one device will conduct in each group. Similarly for group B and similarly for group C. The second rule is that at least every output phase, this was about input phase voltages, but every output phase, assuming that we have an inductive load at the output, we cannot interrupt current through an output phase. So output phase should always be connected to some input phase. In other words, you can say that output phase should not be opened, which means that each output phase should definitely be connected to one of these three. It should be connected to only one, but it should definitely be connected to one output phase. Otherwise, it will be opened. There will be an open circuit condition if I don't keep any of these on, which means that a condition like 0, 0, 0 is not feasible, because 0, 0, 0 will not short circuit the input, but it will definitely open circuit the load, and that is not desired because the load is inductive, and sudden open circuiting of inductive loads is inadvisable. So keeping these two switching rules in mind, we know that in every group only one switch should conduct and at least one switch should conduct, right? Which brings us to the total number of feasible switching states in the matrix converter. So only one device should conduct, either SAA or SBA or SCA. So you have a total of 3 switching states possible for this group, a total of 3 switching states possible for the other group, and a total of 3 switching states possible for the third group, which makes the possibility of 27 switching states. A total of 27 switching states are feasible in a matrix converter, practically feasible in a matrix converter. If you compare this with a voltage source inverter, there you had in each leg you had to make one device conduct, and you had to choose one between 2 devices. In case of a matrix converter, you have to choose one between 3 devices every time, right? Therefore, just like in VSI, one device was a NOT of the other. Here that is not the case, because you have to choose one between 3 devices, right? So because when you are choosing one device between 2, it automatically means that the other device is a NOT of the first device. However, here you have to choose one between 3. Therefore, a direct NOT relationship does not exist in a matrix converter, which also makes the modulation or the control of matrix converters slightly more complicated, because every time you have to make the choice of choosing a device between 3 devices. Also, there are a large number of switching states, which gives you, of course, certain advantages which we will discuss later, but it also makes the modulation or control slightly difficult. Now that we know the switching states of the converter, let's talk about the choice of the device. How do we choose this device SAA? What are the characteristics of this device? Suppose at any time we know that in any group only one device will be conducting. Let me assume that this device SBA is conducting, right? Now when SBA is conducting, it means that this potential VB reaches over this point, right? Over the load point, fine, over the phase A of the load, which means that the voltage across SAA is equal to VA minus VB, right, which is VAB, the line voltage VAB. Similarly, you can see that every switch, whenever the other switch is conducting, the one that is blocking the voltage will be blocking some line voltage. Each switch is rated to the line voltage, and the line voltage can be positive because it's AC, right? It can be positive or it can be negative. Therefore, while choosing the device SAA and also all the other devices, you have to choose a device that has both positive voltage blocking capability as well as negative voltage blocking capability. Let's talk about the currents to be carried by the device. Suppose this SBA is conducting, and when it is conducting, what will it carry? It will carry the load current. Let's call it IA, small a, right? Now this load current that SBA is carrying, which is the load current in AC current, of course, because it's an AC to AC converter, it can be positive or it can be negative. So the currents to be carried by the devices are also positive as well as negative. Therefore, you need a device that has bidirectional voltage blocking capability and bidirectional current carrying capability. This brings us to constructing the bidirectional cell of each device. A very commonly used topology is two IGBTs with antiparallel diodes in a common emitter configuration. So this is commercially available, IGBT with antiparallel diode, and another IGBT with antiparallel diode, such that they are connected back to back in common emitter configuration. It is possible to have other implementations of the bidirectional switch, such as a common collector configuration, such as 4 diodes and 1 IGBT, such as 2 anti-parallelly connected reverse blocking IGBTs, so on and so forth. So what we know is that for now is that the device can carry currents in 2 directions, forward direction and reverse direction, right? And it can block both positive voltages as well as negative voltages across it. Now this was about the choice of the device. Moving on to the advantages of this converter. Why should we use this converter? Classically, it's not a very popularly used converter because of certain disadvantages also and certain complications or complexities in its operation. But what are the advantages? Why would such a converter be used? Generally, if you want to do AC to AC conversion, you first convert AC into DC, and then again through a rectifier, and then you use a DC link capacitor, and then you again convert it into 3-phase AC through an inverter. The advantage of using a matrix converter over the 2-stage AC-DC AC conversion is one, that the converter is inherently bidirectional. It uses bidirectional devices, which means that energy can not only flow from this side to this side, but it can also flow from the load side to the source side. So the load and source are interchangeable. Energy flow is bidirectional. If you're using a motor drive, it is very easily to go for regeneration of the drive using a matrix converter. The second advantage of using matrix converter is that they are very compact in size. The reason that they are very compact in size is because when you eliminate the DC state, you also eliminate the DC link capacitor, and the DC link capacitors, passives like capacitors and inductors, are known to occupy a lot of space, or they have a large footprint, or they contribute to a large volume, large size. But when you're eliminating the capacitor in the DC link, you just have a silicon IGBTs or whatever devices you're using. You only have power electrics. It's a pure power electronic solution, only switches that are converting AC to AC. So it will be a very compact, small sized setup as compared to an AC-DC AC converter. Not only will it be compact, but it will also be more reliable. There have been some research studies that have been done to compare the reliability of matrix converter with AC-DC AC converters. The reason it is more reliable is because the DC link capacitors used in AC-DC AC converters, they are known to have high failure rates or high probability of failing. As a result, when one component fails, that is a DC link capacitor, the entire converter has to be shut down, and then you have to replace the DC link capacitor. In case of a matrix converter, because you do not have anything like an electrolytic capacitor, therefore its reliability is higher, especially as power electronics technology, device technology is improving. Matrix converters have more scope in the future because they are more focused on power electronics or pure power electronics or pure silicon solutions as compared to AC-DC AC converters, which also have some passive components. The third advantage of using matrix converters is that they offer improved power quality on the source as well as the grid side, on the load as well as the grid side, which means not only are the load currents sinusoidal, but it is also possible to make sure that the source currents, that's the currents you're drawing from the grid, they are also sinusoidal in nature. Of course, when you need sinusoidal grid currents, you will also need a small filter at the input over here, which will help you, which will be a very small sized filter, which will help you in achieving sinusoidal grid currents. That is your third advantage. That is improved power quality on the grid side, load side, as well as the grid side. The fourth advantage of using matrix converters is that you have a completely controllable power factor. So even though your load may be something like an induction motor that is drawing reactive power from the system, but somehow you can control the switches in such a manner that the grid does not see that any reactive power is being drawn. So it will you can operate it at unity power factor. You can even use it like a compensator, which is drawing leading wars from the system and compensating for other lags in this lagging loads in the system. So the power factor of the currents drawn from the grid can be unity, it can be leading, it can be lagging. It is basically completely controllable input power factor. There are some other advantages that have been explored recently. That is a possibility to eliminate common mode voltage, but I think discussing that would make this lecture too long, so we can stick to the basic advantages that are known of this converter. Now the next thing that I would like to discuss with you is a brief introduction to space vector modulation of matrix converters. Now, I already discussed with you, whenever we do space vector modulation, the first thing is to draft or just sit down and write all the possible switching states of the converter, which we have already discussed, that there are 27 in number. There are 27 switching states. Now, what are those 27 switching states? Suppose the first group of states that we have are states that sample this at two output phases, they sample the same input phase, and at the third output phase they sample some unique input phase. Let me explain. For instance, a state like A, B. AAB over here means that at output phase A you have input phase A, at output phase B you have input phase A, and at output phase C you have input phase B. The capital letters are representing the input phases which occur at the output phases A, B and C, right? Similarly, another such state, similar state is A, B, A, B, A, A. Or you can also have B, B, A, B, A, B. Or you can also have A, B, B, which means two A's and one B, which are the top three states, or two B's and one A. Similarly, you can have B and C, two B's and one C, or two C's and one B. Similarly, you can have two A's and one C, or you can have two C's and one A, right? If we just add up all the states, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. A total of 18 switching states, right? Where two same input phases and one different input phase are sampled at the output. So these are the main 18 states. Now we are left with 27 minus 18, that is 9 switching states. These are the main 18, or active vectors you can call them. Then you also have the zero states. The zero states are one in which the same input phase is sampled at the output, AAA at the output, or BBB at the output, or CCC at the output. Obviously, in this case, the output line voltages will be zero, because line voltage is what? VA minus VB, that is A minus A, that is 0, or VBC is also A minus A, or B minus B, or C minus C, or 0, and VCA is also 0. So these are the 0 states. Now these 18 plus these 3, that is a total of 21. Most of the time you will see that when you are implementing space vector modulation, you will use only these states, right? Apart from these 21 states, there are some more states called the 6 rotating vectors, which are also used sometimes. They have their own set of advantages, but most of the time they are not used, and I will also discuss why they are not used. These states, 6 states, are those states that switch a unique input phase at the output, which means something like A, B, C at output phases A, B, C, or B, C, A, or C, B, A, or A, C, B, or B, A, C, or C, A, B. So these 6 states, 1, 2, 3, 4, 5, 6, these 6 states are also switched sometimes, but most of the time they are discarded because they result in a rotating space spacer, which I will discuss with you. So let's try to construct the space vector diagram, the line to line voltage space vector diagram, right? Now I'll retain only 3 states because I can't repeat the space vector analysis for all the 18. You can do it as a home assignment, but these 3 states I will retain, only the top 3 states of the 18 vectors. The 0 vectors, I know they will result in a position at the origin because the line voltages are all 0, so I can delete them, right? Let's try to construct the space vector diagram for the first 18 states, out of which we have retained only the top 3 states. Now the space vector of the line voltage space vector is 2 by 3. The output line voltage VAB at an angle of 0 plus the output line voltage VBC at an angle of 120 degrees plus the output line voltage VCA. Please remember the small alphabets ABC represent the output phases and the capital alphabets ABC represent the input phases. Minus 120, right? For this particular state, that is AAB, the space vector can be computed. The space vector is VAB is 0 because A minus A, that is simply 0 at an angle of 0, whatever it is, completely 0. VBC is actually input line voltage VAB. The output line voltage VBC at this time when you switch the state will be the input line voltage equal to the input line voltage VAB at an angle of 120 degrees, right? Plus VCA, it is VBA. VBA at an angle of minus 120 degrees. I can write VBA as minus VAB. If I solve this, I get 2 by 3 into root 3 VAB at an angle of 90 degrees, right? So assuming that this is some constant, let's call it K, the space vector corresponding to this switching state is K times VAB, input voltage VAB at an angle of 90 degrees. Similarly, I can find the space vector for this particular state, and it turns out to be K times again VAB because you're only using A and B vectors at an angle of minus 30 degrees. And if I find it for this third state, it is again K times VAB at an angle of minus 150 degrees. You can do it yourself and find the space vectors. So we are currently doing it only for 3 switching states. Now, the output voltage space vector, the output line to line space vector, is a function of the input line voltage VAB, and if you use the other states, it will be a function of VBC also, a function of VCA also, so on and so forth. Because please remember, right now we have found the space vector of only 3 out of 18 switching states, right? So if I I want to draw the output space vector diagram. If I check the input phase voltages. The input phase voltages are line voltages, they are VAB. At 120 degrees lagging, there will be another phase voltage VBC, and then there will be another phase voltage VCA, right? So there will be 3 phase voltages, each 120 degree apart. And if I'm trying to construct the space vector diagram of the output phase voltages for this particular state, it will be VAB at an angle of 90 degrees. So it will be measured with respect to VAB, but it will be at an angle of 90 degrees, and of course scaled by a factor of K, which is 2 by 3 into root 3. So this is the first state is giving me this vector. But the first state is a function of VAB, and VAB might be positive or VAB might be negative. And when VAB is negative, it will actually give me a line along this, right? So this particular state, AAB, is going to give me a space vector position along this line, either positive or negative. In case of a VSI or in case of a multi-level converter, the input was always VDC. It was always fixed. The input was not changing polarity. But in case of a matrix converter, the input is changing polarity, and as a result of that, whichever state is a function of that input, that state will also result in a space vector that will change polarity, right? So this particular state will give me a space vector diagram like this. Now the second state, if I draw the space vector for the second state, it is VAB at an angle of minus 30. So VAB at an angle of minus 30 is something like this. It is VAB at an angle of minus 30. But again, VAB at an angle of minus 30, whenever VAB is negative, it will give me something like this, right? The third state is VAB at an angle of minus 150. So VAB at an angle of minus 150 is something like this. But when VAB is negative, it will be along the opposite side. That means 3 states are making a hexagon for me. And this is that hexagon. I'm talking about the line voltage space vector diagram, and this is the hexagon of the line voltage space vectors, right? Now, one state is occupying this line, one state is occupying this whole line, and one state is occupying this whole line. How many states are still left? 18 minus 3, that is 15, right? And when I check them, they will also be functions of, might be functions of VBC or VCA at some angle, of course, but they will also occupy the same lines, right? So there are a total of 3 lines, each having 2 positions. That is a total of 6 positions. But each line will be occupied by 6 states. 6 into 3 is a total of 18. If you reconstruct for every state, you take up every state and you find out its space vector, you will see that they occupy the same lines. That means the same output is produced by 6 states in a matrix converter. So there is redundancy depending upon whether that time VAB is positive. These 6 states may occupy either this point or they may occupy either this point, or it is also possible that some of them may occupy this point and some of them may occupy this point, right? But the point is that 6 states occupy this line, 6 occupy this line, and 6 occupy this line. Unlike a multi-level converter, you do not have too many positions on the space vector. You have the same 6 positions like that of a VSI, but there is redundancy. That means more number of states are occupying the same positions. So it has, it is different from a multi-level converter in the sense that it does not occupy large vectors and medium vectors and small vectors. It occupies the same position, but there are too many states that give you the same position. And it is this redundancy which is actually helpful in making the matrix converter an advantageous converter or voltage source inverter, because just like you have the space vector diagram of the voltage source source inverter. You will also have of the load voltages of the converter. You will also have a space vector diagram of the source currents of the of the converter. The source currents will be a function of the, just like the load voltages are a function of the source voltages, similarly the source currents I capital A, I capital B, I capital C will be a function of the load currents IA, IB, IB because of some state, similarly IAAA in case of zero states, or IBBB in case of zero states. And you can also construct a space vector diagram of the source currents of the matrix converter. So you will have another space vector diagram constructed for the source currents. Now you have two space vectors running parallelly, right? And then you whatever source current is desired, a sinusoidal source current, you will check that source current whichever sector it is lying in. There will be 6 states contributing to this vector, and you want particular voltage in this sector. You will combine the two informations. You will see which state, there are multiple states giving you this position, you want this position on the current space vector diagram, and then there are multiple switching states giving you this position which you want in the space vector diagram of the voltage, because you're simultaneously controlling the source currents and the load voltages. Now there are 6 states giving you your best source current, and there are 6 states giving you your best load voltages. You will switch that state which is common to these two, which is giving you the best of both the worlds. This redundancy basically helps you in in controlling both source current and load voltage together. So parallelly both the space vector diagrams are run. I'm not going to go into too much detail because it will get too complicated for you, but if any of you is interested in its implementation, then of course we can sit together and discuss how it is to be done. What my basic point is that in case of matrix converters, because you have redundancy associated with each state, with each space vector position, and we use that redundancy to control source currents as well as load voltages simultaneously. So that was about the space vector of the space vector implementation of the matrix converter. Now, I also want to talk about the nature of the converter. So the input voltages are sine waves. If you want to see the input voltages, the line voltages will be something like this. What basically happens in a matrix converter is that we try to switch the input voltages at the output such that the fictitious rectified envelope, whenever some line voltage is at its peak, we try to trace that particular line voltage at the output, and it becomes a PWM signal sampling this output, something like this, at any frequency that we want from the load. And once a load voltage waveform like this is achieved, load currents will become sinusoidal, 3-phase load currents, and their negative values also if we consider them. Then these sinusoidal load currents, of course if it's an RL load, these sinusoidal load currents are sampled at the input to give us discrete source currents like this, which are again controllable. So load voltage V0 is a controllable switching function of Vs, and source current Is is a controllable switching function of I0. And because the source current is discrete, it has higher order harmonics, therefore you always tend to use a small LC filter at the input of the converter, of course in each phase, so that you can convert this sinusoidal waveform, this discrete waveform, into a sine wave, right? So this is about the nature of the load voltage and the source current of matrix converter. Now, even though the matrix converter offers so many advantages like improved power quality, controllable power factor, bidirectional power flow, and it's also compact in size, single stage AC-AC conversion, then why is it not so popular in case of in industries or in practical implementations? There are many problems associated with matrix converters, and one of the biggest problems which is now solved is the commutation problem. I would also like to discuss this briefly with you because commutation is a big issue when you talk about 4-quadrant switches or bidirectional switches. If you're using this bidirectional switch, which I just showed, that is a basic switching cell of a matrix converter, even if you're using it in some other converter, you are bound to face a commutation problem. Now, what is a commutation problem? Let's take the group 1 of a matrix converter, the first 3 switches. The first switch samples input phase A. These are in common emitter configuration. They switch phase A in at the output phase A, and then they also have anti-parallel diodes like this. So you have something like this, and then there is another switch that switches phase B at the output of the matrix converter, the same phase A. You will similarly have phase C in group A, and it will also be tied to the same output. Now, what is commutation? I'll talk about only these. Suppose you have to transfer current from this switch to this switch. You can also transfer it from this switch to the C switch, but I'm not talking about it right now. I'm just assuming transfer from this switch to this switch. Commutation is nothing but transfer of current. One switch cell turning off and the other turning on, so the current is transferred. This phase A current is transferred from this switch to this switch. Now, suppose let's call this switch as S. Of course, it's SAA, and this is SBA. And we assume that their gates are tied. That means the same switching pulse is given to both the IGBTs of the common switch cell, and the same switching cell is given, the same pulse is given to both the devices of SBA. Let's assume that SAA goes off and immediately SBA goes on, right? This is SAA and this is SBA, and immediately it has gone on, which means that SA will take some time to turn off and SA will have lesser turn on time, because turn on times are lesser than turn off times, and there will be a small interval where both of these will be on, which will cause a short circuit of the source of the line voltage. ये भी on है और ये भी on है, so something like this, current will flow like this, and the source will be short circuited. In voltage source inverters also this problem is encountered कि आपकी एक DC बस होती है और दो complementary switches on अगर simultaneously हो गए तो आपकी DC बस short हो जाती है. In that case, what we generally do is that we give a small dead band, right? And I've already discussed it. We give a small dead band कि एक switch on हो गया, and then after some time the other switch is turned on, so that we can ensure that this switch has turned off safely, and then we turn on the other switch, right? So you avoid any short circuit condition. In case of a voltage source inverter, a dead band is given, or you can say you deliberately create an open circuit condition. And in this open circuit condition, it is also possible that during some time SA has turned off completely and SA has not been turned on. That means it's an open circuit condition. The load current उस time पे कहाँ से जाएगी? There are anti-parallel diodes, right? In a voltage source inverter. अगर लोड करंट आपकी पॉजिटिव है तो वो यहाँ से जाएगी, और अगर लोड करंट आपकी नेगेटिव है तो यहाँ से इस ऊपर वाले डायोड से जाएगी. Which means voltage source inverters have freewheeling paths even if there is an open circuit condition, momentary open circuit condition in the load. But in case of a matrix converter, if I go for dead band based commutation, that means giving a small delay between the two pulses, what happens in the open circuit? Neither this is on, neither this is on. दोनों में से किसी के पास pulse नहीं है. अगर current positive है तो वो कहाँ से जाएगी? The diodes are not connected that they can carry any current. They're connected back to back. You need the current path to be through a switch. So there is no freewheeling path in a bidirectional switch. Is it possible that any current will be carried by the diodes? No, because the diode always needs one switch to complete the path. This diode needs this switch and this diode needs this switch, and when there is no pulse to any of the two switches, it will not conduct. The diode cannot conduct alone. So the absence of freewheeling path in a matrix converter or any bidirectional switch used in any converter for that matter causes a commutation problem. You cannot give pulses next to each other, immediately next to each other, because you know that it will cause a short circuit. You cannot go for deadband based commutation, delay based commutation, because you know there is not a freewheeling path. The load current does not have a continuity, will get broken if you give a delay in current, and because of that break in continuity, an LDI by dt kick will be induced in the load and it will damage your switches. So this was one of the biggest challenges in matrix converters, and when this challenge was solved, I think you can say the biggest problem of matrix converters got solved. And in the future also, it is expected for various applications like electric vehicles, especially electric vehicles, you are going to use these as the bidirectional switch cells, if not as a matrix converter topology, even in DC to DC topologies or AC to DC topologies, it is possible to use this switch cell because of the advantages that it offers. But whenever you have to deal with such switch cell, you have to take care of the commutation. So how do you basically commutate such devices? How do you transfer current from this switch to this switch? The key is that you give separate pulses to all the 4 devices. You don't treat them exactly like these two, like one switch, but you treat them as 2 switches, especially during the transfer of current. When they are conducting, you can give suppose this is continuously conducting, you can give the same pulse. But when you have to transfer current from this to this, you have to give a different sequence of pulses to all the 4 devices. So now I will call this one as SAA plus, because this device is going to conduct the positive A current, and this one I am going to call as SAA minus, because this one is going to conduct the negative phase A current. Similarly, this is SBA plus and this is SBA minus, because this one carries a positive current and this one carries the negative current, right? Now you have 4 devices instead of 2 devices in terms of gating. And what my goal is to transfer current from these devices to these devices, which means that initially both these devices are on. So my state is 1 1 1 and 1, right? And I have 1 1 0 0, because these are off, and I have to eventually reach a state where both of these are off, 0 0 1 1. And this commutation process, I have to do this in 4 steps to ensure that neither there's a short circuit nor there is an open circuit. But for 4-step commutation to take place, this multi-step commutation, iske bahut sare variants are, and there has been 2-step commutation, there is voltage-based commutation, but 4-step current commutation is the most commonly used commutation. It's considered to be amongst the safest, right? So I will basically do one thing. I will measure the load current and I will sense its direction. If the load current is positive, then I know that initially the pulse is going to both SAA plus and SAA minus. But I also know that if the current is positive, then SAA plus is conducting. So the first thing I will do is that I will turn off SAA minus. Okay, so this is SAA plus, this is SAA minus, this is SBA plus, and this is SBA minus. I will turn off SAA minus because I know it's positive current. This commutation is for positive IA. Similarly, there will be a commutation for negative IA. So I will check that the current is positive. So SAA minus is anyway not conducting. So my first step is to turn off SAA minus, and these I will keep off, right? Then I also know that the current IA is positive, which means in the next set of devices, SBA plus has to conduct because the current is positive, right? So I will switch on SBA and SBA minus, SBA plus and SBA minus को off ही रहने देते हैं. So this is my second step, right? Now the third step, अब इस case में if you check the latest step 1010, SAA plus and SBA plus are both on, but they are not going to cause a short circuit because by nature these are in common cathode configuration, or you can say that इनका common emitter point आ रहा है. By nature इन दोनों में से वही एक इस time पे conduct करेगा जिसको ज़्यादा forward bias मिल रहा होगा, depending upon whether phase A is at a higher potential or phase B is at a higher potential. Naturally जिसका forward bias ज़्यादा होगा इन दोनों में से वही एक conduct करने वाला है, right? So there's not going to be a short circuit condition. शॉर्ट सर्किट कंडीशन तब होने का खतरा था अगर आप इस वाले को ऑन कर देते, तो ये एक रिटर्न पाथ दे देता वापस शॉर्ट सर्किट के, बट दिस एंड दिस ओनली वन विल कंडक्ट बाय डिफॉल्ट. Now after that, I will do one thing. I will turn off SAA plus, because eventually my goal is to turn it off. This has already been turned off. This has already been turned on, and this remains 0. And finally, I reach my final goal, that is turning the other last switch also, SBA minus, also on, so that whenever the current becomes negative, this will take over the current as well. So this happens in 4 steps: 1, 2, 3, 4. Current commutation from 1100 to 0011 has taken place in 4 steps, and I have ensured that neither of short circuit will occur nor an open circuit will occur. So I am ensuring safe commutation. Similarly, for negative IA, there will be another sequence, and I'm sure you should be able to do that negative sequence itself. So when 4-step commutation, I think it was given in the year 1990 or 1991 by, in a conference paper by a person called Burani. It was a single author publication, and it really changed the way matrix converters were looked upon, because commutation problem jo matrix converters mein thi, it was a very big problem because it was dangerous for the converter. These converters were not reliable because they had to be provided with extra protections through snubbers or clamping circuits, because the commutation was not safe. There were high commutating voltages involved, LDI by dt kicks involved during commutation, and therefore once this commutation problem was solved through 4-step commutation, it has become more easier to implement bidirectional switches in such circuits. So I decided that I'll also give you a brief idea about 4-step commutation, because you may not use matrix converters, but it's very likely that the future will be based on bidirectional 4-quadrant switches, and you must know that how these 4-quadrant switches are commutated, how they are turned off and how they are turned on. And that is all about 4-step commutation and matrix converters. There's a it's a huge area where a lot of things can be discussed. I've just shortlisted some basic things which I felt you should know. If you are interested more in this converter or its functioning, we can always have discussions on that. So that is all for today. We'll have a last lecture after this on Z source converters, and with that our syllabus will be over. I wish you all the best for the upcoming exams, and take care, stay safe.